In this video, we'll have a look at numerical example for ANOVA. So if we come back to our collapse of blocked arteries case, and we have now the actual measurements of the 3 levels of stenosis, we would like to verify whether there is any difference between the mean values. So if you notice, we have different sample sizes, but it doesn't matter for ANOVA testing. In graphical way, we can see that visually there seem to be differences, but on the other hand, if you look at the spread of those observations within the groups, they overlap with the different ones in here. But on the other hand, for instance, this group seems not to cover as far as the mean value of this third group. So it might be, just from visual inspection, we may suspect that indeed one of the mean values is different from the rest, at least one. But of course, we need the formal test in order to verify it. So let's move on to MATLAB, where I have the data ready. And now we need to prepare the data matrix. So I have all the observations in here. And for the purpose of the function which is ready in MATLAB for testing ANOVA, those observations which are kind of missing, meaning that in some sample there is fewer than in the longest sample, then we just fill them up with none. And MATLAB will handle it in the function. Before we move on to ANOVA, we actually have to test one thing, because ANOVA has an assumption that samples are normally distributed. And the reason is that we are considering sums of squares in our test. And the assumption behind the F-test is that the sums of squares are normally distributed, because F distribution comes from a ratio of chi-square distributions. And we are making a ratio of sums of squares, and chi-square distribution is a combination of squared normal distributions. So n squared plus n squared and so on. So only if this is normally distributed, then the sum is chi-square distribution, and then the ratio has F distribution. Otherwise, we wouldn't be allowed to use ANOVA, and we would have to use some non-parametric test. So that's why testing for normality of your samples is important before you proceed. In the previous weeks, we have done some tests for normality. Here I give you an example of yet one more MATLAB built-in test, which is specifically for normality, and it's Jacques-Berat test. So its name in MATLAB is JB test, and you basically give in that sample. By default, it tests with alpha 0.05. You can also give your own alpha if you want to change the confidence level. But the hypothesis and p-value are given in the same way. So once again, if h has value 0, it means acceptance of null, which in this case means accepted normality, or if it's 1, then it means rejected null. So before we proceed with ANOVA itself, let's run this part and make sure that our data is actually normally distributed. So we can see the h values, first one very high p-value, second one high, and last one as well. So we do have normally distributed data, so we don't have to worry, and we can proceed with ANOVA. So for one-way ANOVA, there is a ready function in MATLAB called ANOVA1, and all you have to do is give it the data oriented in columns. So that's why my X matrix here, it has all the data we had, but I have it transposed so that it actually has 3 columns with the 3 samples. And as I said, in case any samples are shorter than the rest, then you just fill up those spaces in the matrix with nuns, and ANOVA1 will handle that. So as the outputs, you can see, you can check more from help how ANOVA works, but the basic outputs it gives is the p-value for the F-test, and it also shows ANOVA table, and then it gives general statistics which are shown in the table. So now when I run this overall code, we also get a figure which shows now the spreads. It's drawn a bit differently from my graph, but the red lines in here, they represent the mean values, and then these bars there should be representing the furthest observations. So the more interesting part for us now is this ANOVA table, and this one looks like the one we had in the slides. So it collects the information between the groups, within the groups, and then the total. So the sum of squares between the groups is over 200. Within the groups, it's just under 140. And when we add these two up, we will get this total sum of squares. Degrees of freedom are given, once again, it's k minus 1 for groups. So in this case, 3 minus 1. For the error, it's total number of observations minus k. So the result here is 32. And then the total is 34. So it's total number of observations minus 1. Since we had 35 observations, so now it's 34. Mean sum of squares, so we basically divide the sum of squares by degrees of freedom. So it's a straightforward calculation. And then we have F statistic, which is the ratio between these two. So we divide the group sum of square by within group mean sum of squares. So our F statistic is super high, and consequently the p-value is very, very small. So this means practically no evidence to accept null hypothesis. So it does mean that at least one of the groups, one of the mean values, differs significantly from the other two. And usually this kind of information is enough for us. But if you were interested to verify formally which group is the one, then you have to do that studentized range distribution test pairwise. So in here, sample first with second, first with third, and second with third.